BGE Physics. Welcome to another revision lesson with Mr. Bull here. Today we're going to be talking about Key Area 1 space, but part 2. If you've not seen part 1, go back to part 1. We've talked a bunch of stuff that we'll be moving on from today, but make sure you have a wee look at that. Make sure you've got your booklets, got a pen or pencil, and that you yourself are ready for today's lesson. Okay, so we're going to look at 4 things today: sustaining life, mass and weight, gravitational field strength, and life on Mars. All right, now the first one is sustaining life on page 14. So we know that Earth in the solar system is in the solar system, but it's the only planet that has life. There's no moons, there's no planets, there's no comets that have life in the solar system. We also know that Earth is in what we call a Goldilocks zone. Now, Goldilocks zone, remember the tail, nothing too cold or too hot or too much or too little. It's in the perfect zone. And actually Earth lies in the Goldilocks zone in our solar system, but there's Goldilocks zones in lots of solar systems around the universe. So there could be some life there. But we know that we're in the Goldilocks zone on Earth, and it's neither too hot nor too cold. And so the key thing is that it allows for liquid water to be present, because we know that liquid water is one of the key things that we need for life. Okay? So it says liquid water is vital for life to exist, in addition to having a breathable atmosphere, because obviously we have a breathable atmosphere, okay? To grow food, sufficient heat, and light energy from a star. These are all important things we need for life. So, we know that life could exist elsewhere, okay? If the basic conditions were required, such as being in the Goldilocks zone, having a breathable atmosphere, having liquid water, and all of these things, okay? So, is it likely that life will exist elsewhere in the universe? So it says you'll be shown video clips and all of that, but if you have time, you can now go away and do some work on page 14 to record any pieces of information which you think are relevant to this debate. You can go online, or you can research, or you can have books, and you can say in the question, is it likely that life exists elsewhere in the universe? And that's what you should write down. And then whatever you find, make a note of it, and then pause the video and come back in about 5 minutes. Okay, but I'm going to move on now because that's a task for you. Is there life? Very big question, very good question. Now, next one, mass and weight, and that's on page 16. So we're going through this quickly. So mass and weight. Question, how much do you weigh? Okay, if I was to ask you how much do you weigh, what would you say to me? Okay, so just give you 5 seconds. What would you say? What would be your first thing that you would say to me if I said, what do you weigh? I bet you say something like, oh, I don't know, like 60 kilograms. Or maybe you'll say something like, oh, 7 stone or 8 stone, whatever, okay? But that's actually wrong, okay? Because when you say that, oh, how much does someone weigh, it's actually not measured in kilograms. It's measured in a thing called newtons. Now, newtons is a fancy unit for something we call force, okay? But we also know that everyone's weight is different, okay? Well, depending on your mass, that's what we're going to come on to, okay? And it said here, if you've given your answer in pounds, stones, grams, or kilograms, you are incorrect. It's not, it's measured in newtons, okay? But mass is the thing that's measured in kilograms. So what's your mass is the question that you would say, oh, 60 kilograms, or 7 stone, okay? Now, that's measured in kilograms. We make that kg for small, for the units, okay? And it means it remains constant. Your mass will not change. Okay, unless you get bigger, or you lose weight, or you add weight, or you add muscle, whatever, that will change. But your mass, it does not change. My mass here is not changing. But if I was to go to another planet, well, actually my mass wouldn't change even there. If I was to go to the sun, my mass still wouldn't change. Who I am does not change, but your weight does change, and that is the very important thing you need to take away from this lesson. Weight does change, mass does not. Mass stays constant, measured in kilograms. Weight does change, measured in newtons. Okay? Because weight is a force, and it's caused by gravity pulling you down. So gravity is pulling you down, and we know, as I said, it's measured in newtons, that's the unit of force, but gravity is pulling your mass down, and it's what you feel as your weight. So your weight on Earth will be different to your weight on Jupiter, which will be different to your weight on Mars. Because every planet has a different gravitational field strength, or a different force that's pulling you down. And so the more the force is pulling you down, the heavier you will feel. And so therefore the more weight you have. But your mass hasn't changed. Your mass hasn't changed. Okay, so make sure you realize that. Okay, so when people say they weigh, for example, 10 stones or 75 kilograms, they're incorrect as they're actually talking about their mass. We've said that. Okay, that's their mass. So don't get that mistaken. Maybe you can use that with your parents. Ask them what they weigh, and if they say that, then they're wrong, and you can tell them that. Now, sometimes what we can do before we talk about gravitational field strength is that we can measure force, and we measure force by using a spring balance. Okay, now a spring balance is basically a spring that you have a hook at the end, and you pull something down due to the gravitational field of the Earth, and it will show you how much force is being applied due to the gravity. All right. Now it looks like this. It's sometimes called a spring balance or a Newton balance because we know that force is measured in newtons. All right. So that's what they kind of look like there. It's a kind of 2D drawing. We would have done an experiment in class where we'd use different objects and we would put them on the scales and we would see what their weight was. We would obviously know their mass because we'd be hanging it off there, and then we would try and find the gravitational field strength of Earth. Okay, but we can't do that if you're watching this at home. So that's what a Newton balance looks like. Hopefully you've done this experiment in class. If not, then don't worry, it's not too bad. So what we find though is that when we divide the weight of something by the mass of something, okay, we actually get a constant value. So no matter what you have, if I have, this tub here, or I have, a jotter, if I find its weight by using a balance, a spring balance or Newton balance, and divide it by its mass, I will find a constant value for anything, all right? And that constant value is roughly about 10. And that 10 is the gravitational field strength. And that is the gravitational field strength number for Earth, okay? So every gravitational field strength is different for different planets, but for ours, it's 10. So on page 20, when we move to other planets, that gravitational field strength of 10 on Earth changes, so Jupiter will be more, because Jupiter's a bigger planet. For people like Mercury, Mercury's a smaller planet, so the gravitational field strength is now smaller. Okay, for the Sun, it's huge and it's dense, so it has a very large gravitational field strength. Okay, and so that number of the force that you're being pulled down towards the center of the planet is called the gravitational field strength. Okay. Now, as you can see here, I'll talk to you all about that side there, but here we've got gravitational field strength, and we've got lots of different numbers here: 10, 23, 4, 1.6, 11, 9, 270. So we've got lots of different gravitational field strength of different planets. So very interesting here. The Sun has 270, so you would feel incredibly heavy. Our bodies would probably just crush because of the weight, because of the force of that. Whereas if we were on the Moon, we could jump and it would be a long jump because the gravitational field strength is very little. All right. Now that's interesting, but we can actually use an equation in physics that we like to do called weight equals the mass of an object times the gravitational field strength of an object. And we can use this, and we use it in Natural 5 physics as well. And we can shorten it up by doing W for weight, M for mass, and G for gravitational field strength. And we can say that G is equal to 10 newtons per kilogram, because we know that, that's just a constant value that will always be the same. So actually we could probably just say W equals M times 10, all right, for things that are on Earth, all right? So, interesting equation, one that we might have to use at some point in the future. So, let's do a wee example. Just a wee example, a wee maths example here. What would a person who has a mass of 80 kilograms weigh on Earth? So, we know that we want to find out weight. So, weight is equal to mg. So, the mass is 80 kilograms, and we know that. We also know that gravitational field strength is 10 because we just said that it's 10. So, 80 times 10 is 800 newtons. And we have the n there, which is really important. Always remember your units in physics. And an n, capital N, there shows us that it's 800 newtons. All right? So that's the answer there. But then what would happen if they were on Jupiter? So we're going to change it up a little bit. Well, we know that it's W equals mg. We know that the mass is still 80, mass stays constant. But now we know that G, looking at this table, is 23. So we put 23 down there. Now this is a hard calculation. I'm doing it on my calculator, and I find it's 1,840 newtons. Okay? So you weigh more on Jupiter than you do on Earth, but your mass is still the same. Okay, see how you're getting that now? I hope you are. Now, living on Mars, last wee bit. Now this was more of a bigger task in class. It's on page 21. And it is the intention of space agencies to successfully take people to Mars. Okay? Now, this will be one of the most complicated and advanced scientific experiments ever completed because of various factors. Okay? So in the previous lesson, we discussed the effects on the human body due to travel in space. So for example, the gravitational field strength on Mars is different towards an Earth. If you're in space, you don't really have a gravitational field strength, so you feel very weightless, which is not very good for our bone structure. All of these things, okay? But one major challenge is actually the massive distance between us and Mars. And it would take us 600 times further away from us than the moon. And so it will take us a long time to get there. All right? So even though we would like to do it, and we hope we will do it one day, we need someone willing participants to do it, what's going to happen is that we probably will take a long time to figure out how to get there with human beings on board due to distances, due to what's going to happen to the human body, and how we're going to sustain life, how we're going to grow food, all of that stuff. All right? So very, very interesting topic to discuss. But look at your notes, see if you need to fill in anything there. Maybe you need to do some research on that, but that's just a wee thing to get you going. All right? Now, last thing, just to kind of clarify, we know that it would take between about 128 to 333 days to get to Mars using speeds that we could probably get to on a spacecraft, okay? So lots of challenges, lots of things that are going to be stumbling blocks, but things that I think we can overcome at some point in our lifetime to try and get people to Mars, all right? So this here, very interesting, very important stuff, and very real stuff that NASA is doing and SpaceX is doing right now. So that's us for space. Hopefully you enjoyed those last two videos. There was a good revision, good recap, that everything sounded fine and understandable, and I hope you've had a good time watching these videos. BGE Physics, thank you. Hope you've had a good one, and I'll see you in the next video. Bye.